Okay, so let's have a look at the worked examples now, which surprisingly won't probably take as long as the introduction because to get those general rules out there. Now, I'm going to use a similar technique to the previous lesson whereby we use brackets just to focus in on the parts of the expression that need differentiating carefully. So let's do this. So I'm just going to write out the equation again, y equals sine 4x and the rest of it. So it's going to be sine 4x. Now I'll put that in a bracket just to again draw your attention to it. It's going to be sine 4x. That is something we can differentiate no problem using our new rules. Okay, which we've hopefully had a good practice at now. And the second part, of course, is we're going to add 3, and then the new bit is the cos 2x. So I'll put that in brackets as well. Again, you don't have to do this. I'm just doing this to make it really, really clear what we're focusing in on, and also to remove any potential for errors in signs and things like that. All right. So let's first of all, let's differentiate the first bit. We do this term by term, as you know, fully versed in this now. So dy by dx, I think we've got space over here to do it. I'm just going to partition the screen. So dy by dx is going to equal the derivative of sine 4x. Now, if you use the rule from previously, remember that the 4, the coefficient inside the function, migrates to the front. Well, it doesn't migrate. It's copied, and it becomes a coefficient at the front of the function. So it's going to be, first of all, it's going to be a 4. Okay, and then we differentiate the sine part of the function. Now, we just assume it's like sine x. Okay, if we differentiate sine x, we know we get cos x. So that's going to be a cos function. Okay, and then the rule states that we retain the 4x inside the function. So we're going to get 4 cos of 4x. Okay, or you can just use the general form. I've just kind of gone through mentally what the chain rule does, but if you use the general form, it will be k cos kx essentially. So that's the first term done. Now for the second term, we've got plus 3 lots of, now whatever we get when we differentiate cos 2x. And again, it's the same idea. The 2 inside the function becomes a multiplicative constant or a coefficient at the front. So that's going to give us a 2 at the front there. Okay, now if we differentiate cosine, of course, we get negative sine. So perhaps I should have left myself a bit more room there. So it's going to be negative 2 sine, and then we keep the 2x inside the function like that. So again, that's what the general rule would give you. If you differentiated cos 2x, you would get negative 2. No, if you differentiated cos 2x, you would get negative 2 sine 2x, or if you differentiate cos kx, you would get negative k sine kx. So the case now, or what we need to do now is just to tidy this up a bit. So we've got 4 cos of 4x, and then multiply everything inside the second bracket by 3. So that's subtract 6 sine 2x. Okay, and that's the derivative of that function. Okay, for worked example 2, I've just written down the 2 general rules that we're going to use to differentiate this function. Now, you don't have to write these out. You can just reference them or refer to them when you're doing it. You get credit for getting each term differentiated correctly. Okay, you don't have to state which rules you've used. So if you look at the first term in this for this curve, presumably e to the 4x. Okay, we can see that k is going to be 4 in this instance, so we can get the derivative from that really clearly. In the second term, we have a base of 3. It's an exponential function in its own right, so 3 to the power 4x. So the base is 3, so that's going to be the a there that I've highlighted is going to be 3, and there as well. And then the k value is going to be exactly the same as the k in the first part, which is rather nice. So we can see that the k, oops, right there, is just going to be 4 again. Okay, we can't do anything else. We can't simplify it or anything because we have 2 different bases, and it's not a product, it's a sum. So we just substitute in everything, and hopefully we can get the correct answer. So let's do it term by term now. So dy by dx. Okay, so e to the 4x differentiates to 4e to the 4x. Okay, it's something you'll get used to as well really quickly. Okay, no problems there. K e to the kx, where k is 4. And then the second term, we have 3 to the power 4x. All right, so that's going to be plus, and there's no negatives to worry about. So that's going to be the derivative. So that's going to be 3 to the 4x again. We get that back, which is nice. Okay, but this time it's going to be multiplied by k log a. So in other words, 4 log 3. Okay, 4 log 3 is a number. All right, nothing to worry about, and that's the gradient function completed. One thing you could do is if you wanted to write this as a single logarithm, although it doesn't ask you to, we can move the 4 as a power, so it'd be the log of 3 to the power 4. But again, that's not required. Okay, so that concludes example 2. And for example 3, we have something that initially looks quite tricky. Okay, it's going to be another case where we have to use the laws of logarithms. Now, if we just scan over the function that we've been given, we'll get onto the log of x squared in a moment. The second term, though, we have the natural log of 7x. Now, that one is something we can differentiate without much trouble. If I just write down the general form of it that we saw earlier, if we differentiate, this was the one that was slightly anomalous, wasn't it? Because we had some cancellation. But if we take the derivative of the natural log of kx, we saw that you would get k over kx, but that in turn would just simplify to 1 over x. Okay, so that's not an issue. We know what the log of 7x would be when it's differentiated, and the fact it's multiplied by 2 doesn't really matter. There is a problem, though, with the first term, and we'll look at different techniques for differentiating this later in this chain rule topic. But at the moment, we don't have a way of differentiating the natural log of x squared. We're only familiar with multiples of x, not powers of x. What can we do? Well, we can use the laws of logarithms. So if you remember, the laws of logarithms state that if I have the log of some base to a power, like we have here, that power can come down to the front and become a multiplicative coefficient. So that can come down to the front there and multiply the logarithm. So I'm just going to rewrite my function. So this is going to be as follows. So it's going to be 2 at the front multiplied by the natural log of x. Okay, it's exactly the same thing, plus the rest of it, which is, of course, 2 log of 7x. All right, and what I will do is I'll use the brackets again, just so we can draw our attention to the part we need to differentiate. Okay, so it's going to look like that. All right, and seeing as I've just said that, why not put this in brackets as well? So that's going to be 2 at the front, multiplying all that. Okay, now we can differentiate. So you've got more room than you need to here. but it doesn't matter. Okay, so if we differentiate, this is going to be 2 multiplying the derivative of the natural log, which you probably know now is 1 over x. Okay, and then also 2 multiplying the derivative of the natural log of 7x, which again is just going to be 1 over x, as it is for all natural logs of constants multiplying x's. So there we go. So just finish that off. So it's going to be plus 2, and then we're going to have 1 over x again. Now, we just simplify this. We can actually collect some like terms here. So this is going to be 2 over x plus 2 over x. Okay, so we've effectively got 2 lots of 2 over x. So that's going to give us 4 over x. Okay, so that concludes worked example 3. Now this one, number 4, probably looks like the most difficult one we've seen so far. Okay, I'm just going to write it out again. Let's have a closer inspection of what we've got. So it's 2 subtract 3e to the 5x. And so this is a fraction over 4e to the 3x. Now then, this harks back to a technique you used in year 1 when you were differentiating, okay? So for example, just as a bit of revision, we're not going to do this. I'm just going to point out what I'm referring to. So if you had a situation where you had y equals, let's do something similar, 1 plus x cubed over x to the power 5, and you were asked to differentiate that from year 1. At first glance, you would panic, wouldn't you? You would say, well, we don't know how to differentiate this. We only know how to differentiate polynomials, things with integer powers. But we have integer powers hiding in expressions like this. So we can see that I can split this up into 2 fractions. So the first term would be 1 over x to the power 5. And I can do this if there's just a single term in the denominator, okay? Because everything in the numerator is going to be divided by that single term in the denominator. And then I'm going to add x cubed over x to the power 5, like that. So that's the same expression, okay? Note that you can't do this if there's more than one term in the denominator. Or what I mean is you can't divide each term in the numerator by each term in the denominator separately. So just to give you another example, if we had something like this where it was 1 plus x cubed over x to the 5 plus 2, all right, it would be the same thing again. You'd have to divide each term in the numerator by everything in the denominator. So it would look like that. All right. So just so you're aware of that. Now, just to get back onto the example I started at the top, we can actually write this in a way that would differentiate nicely. So we can write the first term as a negative power. Of course, it's reciprocal of x to the, sorry, beg your pardon, it can be rewritten as x to the negative 5, okay, as a negative power. And then if you look at the second term that I've just sort of made up off the top of my head, here there is cancellation, isn't there? So you've got cancellation in the 3 and the 5, okay? So in other words, you could say this is the same as x to the power 3 divided by x to the power 5. And the laws of indices state that you have to subtract the powers when you do that. So that would be x to the power negative 2. All right, so maybe that cancellation part wasn't a good idea when I just did that. Let me just try that again. So that'd be x to the power 3 there. Yeah, so you subtract the powers. So that would be plus x to the power -2. And then you would just differentiate term by term. So that wasn't an issue. We have the same idea here. So if you look at what we've got in this question, we've got 2 divided by the 4 multiplied by e to the 3x first. So let's write it as 2 separate fractions. 2 over 4 e to the 3x, subtract 3 e to the 5x divided by 4 e to the 3x. Okay. Now then, before we carry on, the 4 in the denominator is a bit of a pain, really. You can see in the first fraction that there is going to be some cancellation here. So we'll make sure I state this correctly this time. So we've got 2 over 4. That's going to simplify to 1, and that's going to simplify to 2. Okay, so we've now got 1 over 2 e to the 3x over here. So that's going to be 1 over 2 e to the 3x. And this is something we're going to have to be really careful with in a moment. There's no cancellation in the coefficients on the right-hand side. So I'll just leave that as it is for now. Okay, like so. Now, I just stressed to you that we need to be careful here. What have we actually got? Well, we have got 1 over 2, so that's a half. But you'll notice that we have 3x in the denominator. Okay, so that's essentially saying it's 1 over 2 multiplying 1 over e to the 3x, like that. Okay, and if you multiply those two fractions together, you get 1 over 2 e to the 3x. That's the first thing. Let's just continue and see what we can do with the second term. Well, I can write that as 3 over 4. And the fraction I've got this time, I've got e to the 5x divided by e to the 3x. Okay, and again, you'll see that that gives us the 3e to the 5x over 4e to the 3x. So there's no problems there either. But the question is, what we need to differentiate these. I mean, it's all right playing around with it, but how is this going to help us differentiate? Well, I've got the same situation as I had over here with the 1 over x to the power 5. I can write it as a negative power because it's reciprocated. So the first term is simply going to be 1/2 multiplying e to the negative 3x, like that. And you'll know from experience, when you do complicated differentiation questions, you spend more time with the index laws and the algebra, getting all the prep work done, ready to differentiate, and the actual differentiation is only like 1 or 2 steps. You'll see that quite often. And then if we look at the second term here, we've got the 3/4, and we have inside the bracket. Now, we've got e to the 5x in the numerator, e to the 3x in the denominator. There's a division going on. So if you want to do a little aside over here, you can do. This is e to the 5x divided by e to the 3x. We have the same base. Okay, and we can apply the laws of indices. What do we do with the laws of indices? Well, we subtract, don't we? Okay, that should have been a subtraction. And then if we do 5x, subtract 3x, what do we get? Well, we get 2x. Okay, and that's positive. So inside this, we are going to get e to the power 2x without too much trouble. So there we go. We've rewritten the expression now in a way that we can differentiate it really easily. So now let's perform the differentiation. Yeah, and do take time with this. Go over your laws of indices if you're not sure about them. Okay, very, very important. So dy by dx, now let's do it. It's dy by dx is equal to, well, we keep the half where it is. And I've got the brackets there. I differentiate inside the bracket. E to the negative 3x. We apply our rule. So what happens? Well, it's e to the kx, isn't it? So that's going to be, the k comes down, negative 3 e to the negative 3x. Ke to the kx. Okay? And we're going to be subtracting 3/4. And we've got a slightly easier one on the right-hand side. E to 2x, that's ke to the kx again when we differentiate. So that's going to be 2 e to the 2x. Like that. So that's differentiated. Now, we could, in theory, just leave it like that, but we can see if we can make this look a bit neater. So what do we get? Well, we've got a half multiplied by negative 3. So we've got negative 3 over 2 multiplying e to the negative 3x. Okay. And in the second term, we've got a nice bit of cancelling, I think. We've got 4 there and 2 there. So there's a nice bit of simplification. So that's going to be 2. That's going to be 1. So we get the same coefficient. We get negative 3 over 2. Okay. And this time we've got e to the 2x. All right. And if you want to factorize out the negative 3 over 2, you can do, but I think that looks pretty good. So that concludes worked example 4. Okay, now we're into section B, and so far we've looked at what happens when you use the chain rule to differentiate functions where we have some constant multiplying the x, okay, such as sine 2x or cos of 3x or log of 5x, things like that. But it's quite restrictive, and wouldn't it be great if we could use the chain rule to differentiate composite functions that are a little bit more interesting? And a really nice example is what we've got here, where we have sine of the natural log of x. All right. Notice it's defined for real numbers greater than 0, sorry, because that is the most restricted domain out of the two functions. So sine is defined for all real numbers, but the log of x is only defined for positive real numbers. So we take the most restrictive domain for this composition. All right, so applying the principles that we've looked at so far with the chain rule, it's pretty obvious, isn't it? We're going to have to split it up into two functions that compose together. So u is log of x, the natural log of x, and y is equal to sine of u. So I'll leave it as an exercise for you. So have a go, please. See if you can find dy by dx, given that we've got these two functions. Okay, and I'll go through the solution now. So I should have said pause the video. Pause the video now, have a go, and I'll go through the answer in a sec. All right, I'll go through it now. It's quite disconcerting. I feel like I'm talking to myself, which actually I am doing. So we'll call that equation 1. We'll call that equation 2, if you want to. And let's differentiate equation 1 with respect to u. So dy by du, what do we get? Well, using the rule, okay, this is just going to be the cosine of u, isn't it? Okay. Now, we've defined u already. So if you want to, you could stick the u in there because it's defined here as function 2. But I'll stick to the same method I've used so far. Let's differentiate function 2. So this is going to be du by dx. Okay, and just check you agree with me. So du by dx, another standard result here. This is going to be 1 over x. And I'll just make it clear that this is for equation 1 and this is for equation 2. And to get dy by dx, we combine our two results. So dy by dx is going to equal dy by du multiplied by du by dx. All right, so we multiply everything we've got together. What does that give us? Well, cos u multiplied by 1 over x. At face value, we can't really leave it like that. It's not a good idea to have a cosine followed by some other term. It's always better to have the 1 over x at the front, or whatever it is, the coefficient at the front, so it doesn't look like it's part of the angle inside the cosine function. So I'm going to rewrite that as 1 over x at the front multiplied by cosine of u. And we substitute the u back in. All right, so just to remind you, of course, the u here, okay, is this u that I defined for you when the question was set up. So that's going to be 1 over x multiplied by the cosine of the natural log of x. So rather interesting looking derivative, but that's the derivative nonetheless. So that's how it works. So the chain rule is not restricted to just constants. Yeah, you can compose any differentiable functions together and you can use the chain rule to find out the derivative. So it's a really, really powerful tool. And we're going to use it in a little bit more of a robust kind of way where we can apply it to more complex scenarios. So that's what we're going to do in this lesson. All right, so straight into the worked examples. Right, what have we got here? We've got sine cubed x. Now, just let's familiarize ourselves. What does sine cubed x actually mean? Well, it can mean a few different things, really. It depends how you write it. So we've essentially got sine cubed. So that would be sine x multiplied by sine x. Okay, multiplied by sine x. All right, that's one way to think about it. The product of sine x with itself 3 times. If we want to use the chain rule, though, that's not really a useful way of doing it. There is another rule we could use that I've not introduced you to yet. That would get you the derivative of this if we wrote it like that. But we could also think about it like this. So it's sine of x cubed, isn't it? Now, I wanted to get into that, explaining it in that way, because it can be misleading because of the way sine cubed x is written. You can sometimes forget that it's sine of x cubed. Okay, so you need to be aware that it is sine of x cubed, all cubed. Now, when you see it written like that, it becomes clear that the chain rule is going to be a viable tool. Okay, so what are our 2 functions going to be for composition? Well, if I wanted to cube something, that's fine. I can differentiate that. The sine x is the problem, so that's going to be my composition, the inner function of my composition. So our 2 functions are going to be defined as follows. So we're going to have y is equal to u cubed, and u is going to equal sine of x. And you can compose those together, and we know we're going to get sine cubed x. So let's differentiate. So we'll call this 1, call this 2, and differentiate separately. So dy by du. Okay, so this is year one differentiation, isn't it? Okay, so the power comes down and we take 1 off the power. So 3u squared. Shouldn't be any problems there, I hope. du by dx is a new result, but again, it's a really straightforward one. That's going to be cos x. Great. Okay, what are we going to do with this? Well, let's now find dy by dx. Okay, so we simply multiply them together. So dy by dx using the chain rule is going to be dy by du multiplied by du by dx. Okay, and so this is going to be 3u squared. So it's this part. Okay, that's the first bit. So it's 3u squared multiplied by the second part. So it's cos x, which is here. It all corresponds, of course. Maybe I'm over-egging it a bit, but I just thought I might try and make it as clear as possible. So cos x. Okay, and then the last thing to do is just to make sure it's all neat and tidy and everything is in terms of x. Remember, it's dy by dx, so there shouldn't be any mystery variables in there like u. Now, if we do that, we know we have to find out what the u substitution was. We decided that earlier. That's sine x. That's here. So it's going to be, rather interestingly, 3 sine x all squared multiplied by cos x. Now then, we don't write it like that. Okay, let's write it in the form it was presented to us in the question. So this is going to be 3 sine squared x cos x. That's the derivative. Now then, once you get a bit more fluent with this, you could probably do these in your head without going through all these steps. That's absolutely fine, but until you get used to it, please follow this procedure, okay? Just to avoid any silly mistakes. But yeah, you should start to spot some patterns. So when I'm talking about patterns, you'll notice in your head, you're thinking, well, even though this is something that looks pretty awkward, because it's cubed, you can tell that the 3 will come down to the front, and there'll be something squared, okay? And you retain the function, so you can tell it's going to be 3 sine squared x. Okay, if you treat it like a year one derivative, yeah, you could naively think that the 3 comes down to the front and you take 1 off the power, which is essentially what I've done there. But the trick with the chain rule is the function that's inside, the sine part, you have to differentiate that and tack that on the end as an extra factor. So you differentiate that and put the cosine x on the end. So that's how you would do it in your head very quickly. All right, now in example 6, we're starting to introduce a little bit of context, aren't we? We're trying to find a gradient at a particular point. Now, we have a surd also, and this is a common type of question when we're talking about the chain rule. Okay, you'll see this quite often. So the surd part, that's obviously going to be one of the functions, and then the thing that you are square rooting can be your substitution, your u substitution. So let's define what this actually means, but we'll just rewrite it slightly so we're in a position to differentiate. So I'm just going to rewrite it, not in surd form, but in index form. So we have y is equal to 3x squared plus 1, but raised to the power 1/2. Okay, it's the same thing. We do that because that's how we set it up when we're differentiating. Now then, let's define our two functions. So therefore we're going to have y equal to the complicated bit, which I don't like. So that's going to be u to the power 1/2. Okay. And the u part is going to equal everything inside that bracket, all that stuff. So that's going to be 3x squared plus 1. Like that. Okay. So that's, oops, it's not, my one's not come out very well. There we go. So now we can differentiate separately. So I don't know why I keep labeling 1 and 2. It's not like simultaneous equations, is it? If you keep them together, it's not a problem. So we'll call this dy by du. Okay, now we differentiate this really carefully. So the power comes down. It's year 1 differentiation, isn't it? The power comes down to the front. So the half multiplies the u, and then we have to subtract 1 from the power. So it's u to the power 1/2, but we have to subtract 1 from that power. Okay? And we need to tidy that up a little bit. So this is going to be 1/2 of u to the power negative 1/2. Okay. And again, the question is not presented in index form, and especially not negative index form. It would be a really good idea to rewrite this in surd form. And we can do that now while it's nice and simplified. U to the power negative 1/2. Well, how do we write that in surd form? Well, you could do this in a couple of steps if you wanted to. So this is equal to 1/2 multiplied by 1 over u to the 1/2. Now that deals with the, my maths teacher always told me never to write fractions like that, but there wasn't much space, was there? Yeah, always write fractions with a horizontal line, not a diagonal line. Okay, and u to the power 1/2 is obviously a square root, isn't it? So this is going to be 1 over 2 multiplied by 1 over the square root of u, which you could also, if you want to multiply the two fractions together, this is going to be 1 over 2 root u. So there's lots of steps that have come out of that, but there we go. I think that looks fine. Let's differentiate u now. So we'll do dy by beg your pardon, du by dx. And if we differentiate that, nice and straightforward. Again, it's year 1 differentiation. It's just the fact that it's been put together in a strange way that makes it, or in a composite way, which makes it difficult. So 2 comes down to the front. So that's going to be 2 multiplied by 3, which is 6x. And then take 1 off this power. So that's going to be 6x to the power 1. And then the constant term dies. So that's just going to equal 6x. All right. So we've got our two derivatives. Now let's find dy by dx now. Okay. So combine the two. So dy by dx is going to equal dy by du multiplied by du by dx. Okay, so we multiply them together. Well, we've got the tidied up version, which is 1 over 2 root u, which is here. That's what dy by du is. Remember, that's all equal all the way down to there and to there. So that's what dy by du is. So I'll just write that in. It's 1 over 2 root u multiplied by du by dx, which is 6x. Okay, and you can write that as a single fraction. So this is going to be 6x over 2 root u. And if you just look at that, there's a bit of cancellation going on here. We have got 6 in the numerator, 2 in the denominator. That's going to cancel down. So we've got 1 and 3. So again, a bit more simplification. So this is going to be 3x over the square root of u. And remember, it's dy by dx, so there should not be a u variable in there whatsoever. How did we define u? Well, we defined it all the way over here as 3x squared plus 1. So that would be our final step for finding the derivative. So this is going to be 3x over the square root of 3x squared plus 1. And that's the derivative. Okay, now we're not asked for that. What we're asked to is to find the derivative at a particular point. They've given us the whole, the ordered pairs. They've given us the full pair of coordinates there. Remember, of course, the expression we've got for the derivative is purely in terms of x, okay? So we needn't bother with the y coordinate. That's a red herring. It's just there as a surplus piece of information. So we're simply just going to use the 1 to answer the question. So I'm just going to create a bit of space here just to finish the question off. Okay. So at 1, 2, we know that x is equal to 1. All right, so that's the value that's going to be substituted in. So therefore, dy by dx is going to equal 3 multiplied by 1 in the numerator. And we'll see if we get a nice answer for this actually. Over the square root of 3 multiplied by 1 squared. Sometimes you do, sometimes you don't. Plus 1. Okay, so that's just substituting everything in. So we're going to get 3 over root 5. All right. 3 times 1 is 3. What am I doing? Don't know why I've said 5. Shouldn't record so many videos in one go. My voice is going a little bit. 3 times 1 is 3 plus 1 is 4. That's better. So it's the square root of 4. All right. Yes. So that does simplify nicely, doesn't it? So we take the square root of 4. This is going to be 3 over 2. There we have it. And that's the positive root of 4. Remember, don't be misled to thinking it's plus or minus 2. It's not. If you see the surd, the square root symbol, that's a positive amount. They have to specify whether it's the plus or minus version in the question. Okay, so that concludes that. So the final answer after all that work is that dy by dx when x is equal to 1 is equal to 3 over 2. Okay, moving on to example 7. We have rather an ominous looking function here, or a curve, I should say. I have to get my language right with these. A curve with that equation y equals 1 over 1 subtract the log of 2x, natural log. We have a domain, restricted domain here. Of course, if you're using logs, you can't have any negative values of x or 0. That's not allowed. And we obviously can't divide by 0 in this instance. Right, anyway, so let's get on to the derivative. We have to find the equation of the tangent in this question. So, of course, we're going to need the derivative, and we're given the point x equals 0.5, okay, as a key piece of information, so we know where to draw the tangent, or which tangent to work out. Right. Now, if you look at this, we've got a slight problem in the fact it's a reciprocal, complicated-looking function. It's a reciprocal of 1 subtract the log of 2x. Now, one way to combat this, and this is a common occurrence, you'll see functions like this a lot, equations like this quite a lot, where it's 1 over something complicated. And if you're asked to differentiate it, the way to think about it is as a negative power. Okay, we want to get things in as powers, so equations as powers, so that we can differentiate. Okay, that's the first thing. So the first thing to do is we're going to consider y written in this way. So it's going to be 1 subtract the natural log of 2x. Okay, but rather than as a reciprocal, we'll write it as a negative power. So all that is going to be to the power -1. They are identical statements, so there's nothing wrong with that whatsoever, just a different way of writing it. So that's the first thing to do. Now, when you see it written like that, you can probably sense what the u function is going to be. Okay, the u function is the complicated part raised to the power -1. So we'll write that first. So our u function is going to equal 1 subtract the natural log of 2x. Okay, and the y function, of course, is going to be u to the power -1. Now, both of these functions separately, we can differentiate them without too much trouble. So we'll do the one on the left first. We'll do y. So dy by du. Okay. So remember, we bring the power down. So it's going to be -1, so negative u. And then we subtract 1 from the power. Again, this is where you've got to be careful. If you're taking 1 away from -1, it's not 0. Okay, be careful with that. So it's going to be to the power -2. And we need to present this in a way as it is presented in the question, so without negative powers. So this is, of course, equal to minus, and then we'll write this as a reciprocal, 1 over u squared. Okay, so get all this stuff out of the way first. So this is going to be -1 over u squared, or -1 over u squared, however you want to write it. So that's the derivative of y in terms of u with respect to u. Now, for the derivative of u, we've got the slightly complicated looking natural log of 2x, but remember, we have a standard result for that. We know that the derivative, you can look this up, but the derivative of log of kx, remember, which we derived using the chain rule initially, is just going to be 1 over x. Okay, there's no difference between that and the natural log of x, because the 2 and the 2x will cancel out when you use the chain rule. So the derivative shouldn't be too bad. So du by dx, the 1 will obviously go, and we've got the negative sign to consider. So it's going to be negative, and then the derivative of this part with the negative in front of it. So that's going to be -1 over x. Okay. And there we have it. So now we combine those two results to get dy by dx. So dy by dx is equal to dy by du multiplied by du by dx. Okay, and multiply them together. So that's -1 over u squared multiplied by another negative, -1 over x. And what does this give us? Well, this gives us 2 negatives. Well, again, be careful with this. Negative and negative, they cancel to make a positive. So it's going to be a positive after all that. So it's going to be 1 over x u squared, or u squared x. Quite unusual looking. Now we have to write this as a function of x. So this is going to be 1 over x. And then how did we define u? Well, u is defined here as 1 subtract the natural log of 2x. In fact, I'll just write it again. U is equal to 1 subtract the natural log of 2x, because I've drawn a lot of boxes around it, haven't I? So we put that in, and that's all squared. 1 subtract the natural log of 2x, and then that's all squared. So I'm just going to make my horizontal line a bit longer just to accommodate that. Okay, now that is the derivative. So there's a string of equals there, but that is now my derivative, dy by dx. Okay, all done. But we haven't answered the question, have we? Okay, we have to find the equation of the tangent to see when x is 0.5. Well, we've done the hard work. We've got an expression for the derivative. Okay, so when x equals 0.5, what's the value of the gradient? So we sub in 0.5 into our gradient. So that's 1 over 0.5. Okay, multiplied by 1 subtract the natural log of 2 multiplied by 0.5. So 2 multiplied by 0.5 is 1, of course. So we can see why they've chosen that. This is going to have some nice repercussions. Okay, so that's that. What can we see from this? Well, the natural log of 1 is, of course, just 0. So that bit there, that's equal to 0. Okay, so it's 1 subtract 0, which is just 1 squared, and multiplied by 0.5 in the denominator. Okay, so it's just 1 over 0.5, which gives us an answer of 2. Okay, so that's the value of the gradient of the curve when x is 0.5. This is the same as the gradient of the tangent. So the gradient of the tangent when x equals 0.5 is 2. Okay, so we've got the gradient, we've got the x value, we just need the y value now. So find the y value. Okay, so to do that, we just sub in the x value that we've been given. So x equals 0.5, sub that into our original equation. Again, we're going to get a nice result for this, not going to get anything too nasty. So y is going to equal 1 over 1 subtract the natural log of 2 lots of 0.5, which again is 1. And we've already said that this bit is just equal to 0. So we're going to be left with 1 over 1 subtract 0, which is just, of course, 1. Right, so we've got everything we need. So we've got the gradient, m, which is 2. After all that work, we've got some really nice numbers. We've got x1, we've got the x coordinates, x coordinate, which is 0.5, and we've got y1, the y coordinate, which is 1. This is what's going to go into our formula for the equation of a straight line. Let's sub everything in. So y subtract y1 is equal to the gradient multiplied by x subtract x1. So y subtract 1 is equal to the gradient, which is 2, multiplied by x subtract x1, which is 0.5. Now then, we can be a bit crafty here because it doesn't ask us to give the equation in any particular way. That is an equation that I've just written down of a straight line, so we can leave it. But to be honest, I don't like leaving it like that. I'd like to tidy it up a bit and just be aware that it might ask you to write the equation in a particular way. So we've got y subtract 1 is equal to 2x. And then we've got 2 multiplied by the 0.5. The negative 0.5, if you like. So that's going to be negative 1. And it's going to be a nice equation as well, isn't it? Okay. Let's add 1 to both sides. So y is going to equal 2x. Wow. Okay. So that's the gradient. Sorry, that's the equation of the tangent, which is what we, when x is 0.5, which is what we were asked to find. Okay, so that concludes example 7. All right, so final example in this section, we have another reciprocal function, this time with a squared in the denominator. What we're going to do here, well, we're going to rewrite it using exactly the same principle as the previous example. Okay, so it's a good opportunity just to practice this style again. So if I just rewrite it, so we're going to consider the following way of writing y, where we use a negative power instead of a reciprocal function. So it's going to be y is going to equal 2x cubed plus 1. And then this time it's going to be raised to the power negative 2. Okay, so this is the same thought process as the previous example, and this is a good approach when you're using the chain rule. Okay, there's different techniques, of course, with the chain rule. This is one of the main ones. So what have we got now? Well, we've got to define our y function and our u function. Well, we can see the complicated bit is inside the brackets. So that's going to be u to the power negative 2, isn't it? So let's define our u function first of all. So u is going to equal the 2x cubed plus 1. And then we just define the y function as u to the power negative 2, as it states there. Right, okay, so we're on our way. So now we've just got to differentiate accurately. So start with dy by du. Okay, and this is year 1 differentiation. So bring the negative 2 down and subtract 1 from the power. Again, just be very careful. If you're subtracting 1 from negative 2, okay, that's going to give us negative 3, not negative 1. Just be very careful with that. And let's rewrite this again as a reciprocal function. So it's going to be negative 2 multiplying 1 over u cubed. Okay. Okay, put those two factors together. That's going to be negative 2 over u cubed. And if you want to, you can put the u back in. Okay, but I'll just leave it like that for now. On the right-hand side, we're going to differentiate u now. Okay, so du by dx. Again, year 1 differentiation, it's just the process is year 2, isn't it? 3 multiplied by 2, which is 6, x to the power 2, take 1 off the power, and the constant term will go. Let's put everything together now. So therefore, dy by dx is going to equal dy by du multiplied by du by dx. So we find the product of 6x squared and negative 2 over u cubed. Not too bad, really. So this is going to be negative 12 x squared over u cubed. Just multiplying those together. Okay. Hope that's not too much in one step. Or maybe I should just put in brackets what I've just done. So that'll be 6x squared multiplied by negative 2 over u cubed. Okay. Right. And then we can substitute in the u now. So that's going to be negative 12 x squared over u cubed. Now, u is the 2x cubed plus 1, as we defined earlier, or just here. So that's now going to be cubed in the denominator now. So notice the derivative is getting more complicated. So let's put that in. So that's going to be 2x cubed plus 1. So that's u to the power 3. So there's our derivative. Okay, now why do we need the derivative? Well, this time we're going to find the equation of the normal to see at the point where x is equal to 1. Okay, so there's key information there. So we need to find the gradient of the norm of the curve when x equals 1, and then we can find the normal. So when x is equal to 1, what's the value of dy by dx? Well, we just substitute 1 into our expression for the gradient. So it's 12 multiplied by 1 squared, okay, divided by, it's going to be 2 multiplied by 1 cubed now, okay, plus 1. Okay, we close the bracket, and then all that is raised to the power 3. There we go. Right. So we've got negative 12 in the numerator. And we have 2 lots of 1 cubed. So 1 cubed is, of course, 1. Double that is 2. Add 1 is 3. 3 cubed is 27. All right. So we've got negative 12 over 27. That does actually simplify. There's a common factor of 3 in there, isn't there? Okay. So common factors of 3. Well, we've got 3 multiplied by 9 and 3 multiplied by 4. Okay, so we've got negative 4 over 9. Now, this is where you can make a mistake. That's the gradient of the tangent. Okay, so let's just make a note what we've got. So the gradient, in fact, let's just sort of make it a bit more succinct. At x equals 1, the gradient of the tangent is negative 4 over 9. That's what we've just discovered. So we need the gradient of the normal. So therefore, gradient of the normal is going to be the negative reciprocal of that. So change the sign and flip it. And it's the norm. Remember, it's the normal that we wanted. It's this which we're asked for. So it's the gradient we're going to use is 9 over 4. If you forget to do that, obviously it's going to make your equation wrong. Okay. Now we also know that we're considering the point where x equals 1. So we're going to need the y coordinate for that. Let's do that. So when, in fact, I've just said we're talking about x equals 1, aren't we? So the y coordinate is going to be using the original function up here. Okay, so we just sub 1 into all that. So that's going to be 1 over 2 multiplied by 1 cubed. Okay, plus 1, and then the whole thing is squared. All right, so let's see what we get. So this is going to be 1 over 2 lots of 1 cubed again. So 1 cubed is 1, multiplied by 2 is 2, add 1 is 3. So that's 3 squared this time, which is 9. Okay, so that's the y value. So let's just make a little summary of the information we've got that we can use for our normal. So what do we know? Well, we've got the gradient is 9 over 4. We've got the x coordinate, which is 1, and we've got the y coordinate, which is 1 over 9. So that's all the information we need to find the equation of the normal now, and we use the same formulas we used in the previous example. And I'll just for completeness, I'll call that x1 and y1, okay, because we're going to sub it into that equation formula, sorry. So we've got y subtract y1 is equal to the gradient multiplied by x subtract x1. So y subtract y1, which is 1 over 9, is going to equal the gradient, which we discovered was 9 over 4. Okay, and then we have x subtract x1. And x1 is, of course, just 1. Right. Now then, let's say you're doing an exam. Time is of the essence. Do we have to express this straight line in a particular way? Well, in this instance, I'm going to say no. I think I rearranged the last one. This one's going to take a few more steps to write every coefficient as an integer, which is not necessary. You're not asked to write the straight line in any particular way. You will get full credit for stating this as an equation. All right, so this would constitute the equation of the normal. And I think that concludes the example. So we're just going to take a slight detour and introduce a new variation on the chain rule. So a special case, if you like, whereby the independent and dependent variables swap over. In other words, what I mean is if we have x as a function of y as opposed to y as a function of x, as you can see here. Okay, now if that happens, you might still be asked to find dy by dx. Okay, but dy by dx, as you can see here in the example we're going to do in a second, is predicated on y being the dependent variable. Okay, so this is the dependent variable, which is usually, in cases we've seen so far, when y is the subject of your equation, and x here is the independent variable. So we're going to look at a way of finding dy by dx when the opposite is true. So y and x are swapped around. Now, there's a more complex way in which this can materialize, which we'll look at later on in this chapter when we look at implicit differentiation. But for now, we're just going to look at cases where we have x as the subject, as you can see here, and it's defined as a function of y. So it's the right-hand side is all in terms of y. So we can just differentiate, as we have done using the chain rule, as normal. So what I can do in this situation is I can just find out what dx by dy is. Okay, so dx by dy. Now I have to do it like that because x is my dependent variable here. Okay, so see how they correspond, how I've just highlighted them there. And y, as you can see here, this is the independent variable, so that goes on the bottom. All right, so we have to write dx by dy. We have no other choice in this situation. And we would just differentiate this as normal. So I would just differentiate this as 2y. So bringing the power down and taking 1 off the power. And then same for the next term, bring the power down and take 1 off the power, subtract 1 off the power, in other words. So I get that. So I get dx by dy is equal to this. So how would we find dy by dx? Well, if I reciprocate my dx by dy, that would give me dy by dx, wouldn't it? It would just be a simple case of writing it as 1 over dx by dy. So that's what we're going to do. So we're going to find the reciprocal. Okay, so in finding the reciprocal, we're going to have 1 over dx by dy, which is on the left. This is the left-hand side of this derivative. Okay, is going to equal 1 over the right-hand side. Okay, so there we have it. Now, to get dy by dx, of course, if you look at the left-hand side, I can multiply the top and bottom by dy. So if I multiply by dy there and by dy there, we get the clearing of the dy in the denominator. So this cancels out and we get dy by dx. Okay, and I haven't changed anything about it. So this is my final answer. My final derivative is going to be dy by dx is going to equal 1 over 2y plus 3y squared. Now, that's the best we can do. You'll notice there's a weakness in finding a derivative like this, namely that we don't have any x variables on the right-hand side. It's all in terms of y. Okay, and remember, we don't really want that. We want, if we found the derivative of y with respect to x, we're expecting some function of x, aren't we? But we can't do it in this case. Okay, what we'll need to know, we need to know something. If we're finding a tangent or a normal on the curve, we would need to know what the y coordinate is in order to, at a particular point, in order to find the derivative at that point. So it is a slight weakness in that we don't have this in terms of x. Okay, one way you could do it is to make y the subject in the original equation, but that would be rather ominous looking in this situation. So we're just going to leave it like that. And I've just provided you with a space here just to write down this as a rule. So if you want to find dy by dx, and you have a function defined as follows, so as x is equal to some function of y, like that, dy by dx would simply just be 1 over dx by dy. Okay, so you would find dx by dy by differentiating your function and then reciprocate it. So just to finish that little example off, just make this look really important, because this is going to be useful in the next worked example. All right, so maybe just put it in a box, highlight it, whatever it is you like to do to make these things look important. Okay, and then we can do a worked example using this technique. All right, so we're going to do one example using dx by dy as our derivative. And you can see here we've got a curve C with the equation x is equal to, let's get rid of that, x is equal to e to the power cos y, cosine y, defined for all real values of x. Now, we've got to show the equation of the tangent is given here. We've got to show this. So we're going to have to find the derivative. We need to find dy by dx. All right, so that's our aim. Or our first aim is to find dy by dx. Okay, once we have dy by dx, we can establish what the gradient of the curve is. Now then, we need to differentiate. At the moment, we've got a complicated looking function. So I'm going to have to use the chain rule to find a composition of two functions. So at the moment, I can see that the thing that's putting me off is the cos y in the power. It's making this look really, really difficult. Now, wouldn't it be great if we could remove that? Well, of course we can, because we've got the chain rule. So I'm going to say x is going to equal e to the power u. Okay, and my second equation, u must equal cos y, cosy. Right, So just check that that makes sense. If you substitute the u into the equation for x, yes, we're going to get e to the cos y. Now let's apply the chain rule. So we're going to differentiate both of these equations with their respective variables. Now, as you can see, we're going to have to be careful with the letters. We have x as the dependent variable there. We have u as the dependent variable there. And we also have u as the independent variable in the left-hand equation and y as the independent variable in the right-hand equation. So let's find out what dx by du is. So dx by du, so I just differentiate it with respect to u. It doesn't change. It's just going to be e to the u. And just so you can see the correspondence of the variables, remember the dependent variable goes, the independent variable goes on the bottom in the denominator, and the dependent variable goes in the numerator. Okay, so let's differentiate the second function, u. So it's going to be du over dy this time, just being really careful with the letters. So once again, we have we have the independent variable in the denominator, and we have the dependent variable in the numerator. Okay, and we can just differentiate as normal. So if we differentiate cosine with respect to y, we're going to get negative sine y. Okay, so there's nothing too ominous about that. Let's put it all together using the chain rule, and we can find dx by dy first, I think. So dx by dy. Now, I'm going to need a dx in the numerator. Okay, so it's going to be dx by du multiplied by du by dx. Sorry, du by dy. Okay, and then the du's will cancel, as you can see, and I get dx by dy. So we've eliminated that u variable from the derivative. So we'll put those in now. So it's going to be e to the u multiplied by negative sine y. So we just need to make this look a bit better. We don't want any u variables in there. It's all got to be in terms of x or y. So in this case, y. So this is going to be negative e to the u. Remember, u is cos y multiplied by sine y. Okay. So that's all good. Now we've got the derivative. Now that's dx by dy. Okay. To get dy by dx, so we're just going to do an implies. We need another step here. So dy by dx is going to be the reciprocal of what I've just found. So that's going to be 1 over all that, and it's negative. I'll put the negative in the denominator. I'll keep it there. Negative e to the cos y multiplied by sine y. Okay, so whatever you do, do not forget that step. So this is the gradient of the curve. Okay, that we've just found. So that's dy by dx. Right, now then, we're given a y coordinate, which is very useful because we're going to need it. We don't have any x information here, although we could find it using the equation. We're given the y coordinate as pi over 2. Okay, that's fine. So let's substitute that into our dy by dx. So we're going to sub y equals pi over 2 into dy by dx. Okay, that's what we're going to do. Now, if we do that, what do we get? So we get dy by dx is going to equal 1 over, don't forget the negative, e to the cos of pi over 2. Okay, obviously this is in radians, multiplied by sine of pi over 2 also. All right, and that's in the denominator. I'm just going to extend my separating line in my fraction. So there we have it. Right, so we just need to evaluate cos of pi over 2 and sine of pi over 2. So I hope that won't be too taxing. So it's, remember, pi over 2 is, of course, 90 degrees. So what's the cosine of 90 degrees? Well, that's going to be 0, isn't it? So we know that that part is equal to 0. Some equal signs there. That's equal to 0. And sine of pi over 2 is where the maximum of sine occurs, or local maximum. So that's equal to 1. So nice numbers, nothing too complicated. Right, so if we just tidy that up a little bit, we're going to have 1 over, now it's negative, e to the power 0. Well, anything to the power 0 is, of course, 1. So there's no problem there. So that's going to be negative 1 multiplied by 1. So it's just going to be negative 1, isn't it? So that's the gradient of the curve at the point where the y-coordinate is pi over 2. So we've got that. So that's an important number that we've just figured out. Okay, so we've got the gradient. Now, just reading the question again, what do we need to do with this information? Well, we need to find the equation of the tangent. All right, so we've got the equation of, we've got the gradient of the tangent already. So the gradient of the tangent, we don't have to do anything with that value. We now know it's just going to be negative 1. And we need 2 coordinates. So we need the y-coordinate and the x-coordinate. We've got the y-coordinate. So we need the x-coordinate. So when y is equal to pi over 2, how do we find the x-coordinate? Well, we go back to our original equation up here. So it's going to be e to the cosine of pi over 2. Okay, so e to the cosine of pi over 2. That featured in the denominator of the derivative, didn't it? We know that's 0. So it's e to the 0, which is, of course, 1. Okay, so we've got all the ingredients now. We've got the gradient, we've got x, and we've got y. So let's substitute them all into the equation of a straight line. So again, I'll just make a list of what we have. So we've got m is equal to negative 1. We have got x1, which is the x coordinate, of course. This is going to equal 1. And the y coordinate, y1, is going to equal pi over 2. And this is all the stuff we're going to sub into the formula, okay, or the equation of a straight line. So let's do that. So we have y subtract y1 is equal to the gradient multiplied by x subtract x1. Okay, subbing everything in. So therefore, y subtract y1, which is pi over 2, sub that in there, is equal to the gradient, which is negative 1. So glad these numbers are really straightforward. Always helps, doesn't it? And then we have x subtract x1. So x1 is, of course, just 1 as well. So all those are substituted in, so that's really good. Now, we just have to hopefully make this look like the answer that it's provided for us. It's a show that question. I've not really had my eye on that. I'm just trusting the mathematics. So let's rearrange this. So we've got to expand the brackets and rearrange it. So we've got y subtract pi over 2 would be equal to, now if I expand the bracket, that's going to be negative x. And we have the double negative, so be very careful. We have the negative 1 and the negative 1 there, so that's going to be plus 1. Like that. And we need the x and the y's on one side. Okay, so I'm going to add x to both sides. And I'm going to add pi over 2 to both sides. And as you can see, just a bit of rearranging, we get the desired result. Okay, so it's quite an elegant looking equation of a tangent. And I think that concludes the example.